Hello everyone, today I will be talking about angular momentum. Angular momentum is defined as the moment of momentum about a point. So it is defined as the moment of momentum. So it is quite a mouthful, a moment of momentum. We already know what momentum is. Momentum is mass times velocity. So that's momentum. And now we are going to take a moment of that momentum. And definition of a moment is R cross the quantity. So R cross mv. And we call that angular momentum, and we show it by h. And because R is a vector, the velocity is a vector, the result of a cross product is a vector as well. When we are finding a moment, we have to find it about an axis or about a point. That's why usually the angular momentum gets a sub-index or any point that we are writing a moment about. So if we have an object here with mass m, if it has a velocity, therefore it's going to have a momentum. And that momentum can have an angular momentum about an axis or about a point. R cross v, R cross mv, the moment of momentum. So if we want to write it in a cross product format, HO is I, J, K. The first row is I, J, K. The second row is the component of your first vector, which here is R. So that would be Rx, Ry, and Rz. And the third row would be your second vector, Vx, Vy, and Vz. And there is mass as well, which is a scalar. If you want to expand that, I just remove the first column and the first row, so that would be Ry times Mz, Mvz minus Rz times Mvy. And J, similarly, we remove the second column and the first row, Rx Mvz minus Rz Mvx plus K, the last component, we remove the third column and the first row, so Rx Mvy minus Ry Mvx. As our angular momentum is a vector, therefore it has three components, I, J, and K in three-dimensional problems. So the other definition would be HO dot, which defines the time rate of change of angular momentum. So that's time rate of change of the particle's angular momentum. So let's expand that. H dot refers to derivative with respect to time. So d over dt of h. What is h? Is rmv. So d over d of r cross mv. So we have two components, and we are going to find the derivative of these two components. So we have to find the derivative of the first component times the second component plus the derivative of the second component times the first component. So let's do that. Derivative of r dr with respect to dt cross mv, that's the first term, plus now we just keep the first component and take a derivative of the second component. M is a constant, and then dv over dt. So if we look at the first component, dr over dt would be the velocity. So velocity cross product mv. What would be the cross product of a vector by itself? It would be 0, because the two vectors are parallel, and two parallel vectors, the result of the cross product would be 0. So the whole term goes away, and we only have the second component. So in the second component, dv over dt, that's the definition of acceleration. So h dot will be simplified as r cross ma. Now we are going to talk about another definition. Principle of angular impulse and momentum. Principle of angular impulse and momentum. Similar to linear impulse and momentum, we started by second law of Newton. Summation of forces equals ma. And then we said a is derivative of velocity over time. Therefore, summation of forces dt would be m dv. And if we take an integration of both sides, we get f dt, we call that an impulse, equals m v2 final velocity or final momentum minus initial momentum. So that was impulse, and these are momentum. That helped us a lot when the force is given as function of time. Now we are gonna expand it to find a relation for angular impulse and angular momentum. All we need to do is multiply each side by r and have a cross product. So r cross f dt, r cross m dv. So if you look at each side, r cross f is the definition of moment, and r cross m dv is the definition of angular momentum. So we can write m moment dt equals h2 minus h1. We call this angular impulse. And we call this angular moment. Between time t1 and t2. So remember, the angular momentum is the moment of momentum, is r cross momentum. So when the angular impulses acting on a particle are all 0 between time interval t1 and t2, when m is 0, then all we have are the angular momentums, the initial and final. So we can extend this for a special case that m is 0, and therefore we have conservation of angular momentum. So when the angular impulses acting on a particle are all 0 between time interval t1 and t2, the angular momentum is conserved. And then we can write h O1 for our system is equals to h O2 for our system. When there is, in the absence of angular impulses, the initial and final angular momentum are going to be the same. We have to remember this is the conservation of angular momentum, which is not equivalent to the conservation of momentum. There are some cases that you might have conservation of momentum, but not conservation of angular momentum, or the other way around. Here we are dealing with our cross product. So if the forces are parallel, we might not have any angular momentum while we are going to have impulses. Now let's solve a problem. The first problem that we are going to solve, if we look at the first problem, each ball has a negligible size and a mass of 10 kilograms. So there are two balls, each has a mass of 10 kilograms. So the mass is 10 kilograms. So the unit is SI, and it's attached to the end of a rod whose mass may be neglected. So we're going to neglect the mass of this rod. If the rod is subjected to a torque mt squared plus 2, so the torque is given as function of time, which makes the integration over time very easy, where t is in seconds, determine the speed of each ball when t equals 3 seconds. So we have the initial speed, the speed of 2 meters per second when t is equal 0. So we have v1. We're going to find v2, the final speed. And we have the radius, so we can find the angular momentum about the axis. We can call this axis O. And we can write conservation of angular momentum because there is a moment acting on our system. But we can write the principle of impulse and angular momentum. So the principle of impulse and angular momentum that we just talked about. The principle is saying that the initial angular momentum about an axis, call it O, plus the angular impulses on our system during the time period of interest, which for us is from 0 to 3 seconds, would be equal to the final angular moment. So the initial angular momentum is R cross MV1 and R1 plus 0 to 3. The moment is given to us here. as function of time, which again makes it very easy for us to take an integration of that equal the final. So here we have R cross mv in a vector form. We can change it to a scalar form by R mv sine of the angle between the two. But here we know the velocity and R are perpendicular to each other, which means that sine theta is 1. Plus, let's take an integration here, would be t cubed over 3 plus 2t, and we have to evaluate that between 0 to 3. Similar here would be R2 and V2 sine of the angle, which would be 1 here for perpendicular case. So we're just going to plug in the values. Let me write the sub indices as well. So R1 is 0.5, is not changing. I have the mass, which for this case is 10. The velocity, which is given as 2, the initial velocity. And here, one thing that we need to be careful is that we are writing the principle of impulse and angular momentum for the whole system. So for the whole system, we have 2 masses. So we have to write 2 here as well. Plus 3 cubed would be 27 over 3. Plus 2 times 3 would be 6. Minus 0, which would be 0. R2 is not changing. Again, we have 2 masses, so we have to write 2. R is again 0.5, M is again 10, and we are trying to find V2. So in that equation, the only unknown is the velocity. So V2 would be 3.5 meter per second. So we started by a velocity of 2 meters per second. We applied angular impulse on the system, and the final velocity is 3.5 meters per second. So the velocity has increased from 2 meters per second to 3.5 meters per second in 3 seconds. Okay, let's move to the second problem. So you can pause the video and read the problem and try to solve it yourself, and then play it again to see my solution. So a 4-pound ball B is traveling around in a circle of radius R1. So the initial R1 is 3 feet. With a speed of VB1 is 6 foot per second. If the attached cord is pulled down through the hole, so the attached cord is being pulled, so the radius is not going to remain constant. This radius is changing as the rope is being pulled down through the hole with a constant speed of 2 feet per second. So we have VR is 2 feet per second. So we have 2 components of velocity here we need to be careful of. For this mass M, for our object, there is a velocity towards the center, we call it VR, and there is a velocity perpendicular to the radius. We can call it the tangential velocity. Sometimes it's called V theta. The symbol that we use is not really important, but the concept is very important that we have 2 components of velocity. Determine how much time is required for the ball to reach a speed of 12 feet. So we need the time that velocity is going to reach 12 feet per second. So here is given the velocity 12 feet per second, and there is no indication of which component of velocity we are talking about. So that means it's the magnitude of the velocity, or speed also indicate that we are talking about the magnitude of velocity. So time is one of the unknown. How far R2 of the ball is from the hole when this occurs. So we want to find R2 as well. So looking at the problem, this is a classical problem for angular momentum. First, to judge whether we can use conservation of angular momentum or not, we have to draw a free body diagram to see whether we have conservation of angular momentum. So free body diagram of our ball B. If we have a mass here, the weight is acting downward, then we have the normal force, and then we have the tension of the rope. And here would be our point O that we are going to write our angular momentum equation about. So looking at this free body diagram, we have three components of the force. We have to evaluate whether any of these components are creating a moment about point O. N and mg are parallel to the axis of rotation. So they're not going to create any moment. Because remember, the equation is R or R cross F. For this to be valid, to have a value for R cross F, first of all, we need to have R, there needs to be a distance. And second, we have a cross product. So for the angles 0 and 180, this value becomes 0. So here, these two are parallel, so the angle between the axis and also the forces would be 0. So they're not going to create a moment about axis. Let's call it AA. Force T creates a perpendicular angle with axis AA, but there is no R, so it's going through the axis. So whether the forces are parallel or going through the axis, they're not going to create a moment. Therefore, none of these forces are creating a moment about our axis of rotation. Therefore, we can write conservation of angular momentum. So if you write conservation of angular momentum, we have H, let's call it AA1 is equals to H, angular momentum at the second instance. Again, R cross MV, R1, MV1 equals to R2 cross M, V2. These are all vector. So the radius is changing and the velocities are changing. So the mass is not changing. Yeah, so I can cross out mass, so I don't deal with mass. And it's a cross product, so R cross V. So the radius for one is 3 feet. Cross product with the velocity, which means that velocity times sine theta. So if you look at the velocity here, this velocity is not going to create, or here it's better to show it here. The velocity is not going to create a moment about the axis, but the tangential velocity is creating a moment. So whenever we are writing the conservation of angular momentum equation, we need to know which velocity is actually creating a moment. The tangential velocity is creating a moment, and the initial velocity is given to us at 6 feet. And sine, which would be 1, equals R2, which we don't know. That's the unknown. And the final velocity. So the question has given us the final velocity. The question has told us the final velocity or speed is 12 feet, but that's the magnitude, that's the total velocity. We need to find the magnitude of the tangential component. So we know if we have the total velocity and we have each component, if we have VR and tangential component, if we have the total magnitude and we have the radial component, we can find the tangential component. Here V is 12, VR is 2. We just need to find VT. So the tangential component of velocity would be 11.83 foot per second. And that's the component that we are going to use in our equation here. So the only unknown would be R2, so we can find the final radius, which should be 1.52 meter. So as we are pulling the rope, we started by velocity of 6 feet per second, and we ended up with a velocity of 11.83, but the radius has changed, but the angular momentum remains the same. 3 times 6 is the same as 1.52 times 11.83. So the radius has decreased, but the tangential velocity has increased. So that's one of the unknown that the problem is asking for, the final radius. The other unknown is the time that it takes. And we know the tangential, if we have VR, is simply delta R over the time that it takes. So delta T would be delta R over VR. So initial was 3 feet over 1.2, and I have to correct this. The unit is now meter, the unit is feet. Delta T, delta VR, which is the radial velocity that is given to us as feet per second, and the unit here is feet. So 0.74 seconds. So it takes 0.74 seconds for the velocity to change from 6 to 11.83, and also the radius changes from 3 to 1.52. So if we go back and look at our solution, there are a couple of important points that we need to pay attention. One is whether we can write conservation of angular momentum. And we observe that we can write it about the axis of rotation. None of these forces are going to create a moment for us. These two, they're not creating any moment because they're parallel to the axis, and T is not going to create a moment because it's going through the axis. When it goes through the axis, means there is no R. When they are parallel, means the sine of the angle between the two would be 0. Then we can write the conservation of angular momentum equation. And once we write the conservation of angular momentum, the mass is cancelled out. So it's just a ratio between R and V. The only unknown was the velocity that we found out. The only unknown was the radius that we found out. To put in the velocity, we need to know which velocity is actually creating a moment. The tangential velocity is creating a moment. So we need to write the correct component. We didn't have the component, so we found the component. We had the overall magnitude. We had the radial component. That's the rate that the rope is being pulled. We found the tangential component. We plugged in the correct component of the velocity. We found the radius, the time that it takes. We have VR, and which we have the change in R, so we can find the time. Now let's move to the third problem that we're going to solve today. Again, I would recommend to pause the video, read the problem, think about the problem, and start solving it. and then you can play the video again and look at my solution. So let's read the problem together. A box having a weight of 8 pounds is moving around in a circle of radius RA 2 feet. Always like to write the known values in one place so I know what I have and what I'm looking for. With speed of 5 feet per second. So VA is 5 feet per second while connected to the end of a rope. If the rope is pulled inward with a constant speed of VR, so this is the tangential component, it doesn't have any other component, and then we start pulling the rope. And that's constant. So for both instance A and B, the rate of pulling the rope would be the same. Determine the speed of the box at instant RB (1 foot per second). 1 foot. How much work is done after pulling the rope from A to B? So we want to find U from A to B, the work that is done on the sample. Neglect friction and the side of the box. So when we look at the problem, we have a mass here, we have a velocity, so we have a momentum. There is a distance, so we are going to have an angular momentum as well. So we have everything at point A, but at point B, we want to find the velocity at point B. Let me write one of the velocity at point B as an unknown, the tangential component. And we have the radius. So to evaluate whether we can write conservation of angular momentum, we need to draw a free body diagram. So free body diagram of box A. Let me. So we have the weight, mg, we have the normal force, and we have the tension, and we are going to write the conservation of angular momentum, or evaluate whether we can write conservation of angular momentum about axis OO. So similar to the previous problem, N and mg are parallel to the axis, T is going through the axis, so none of them are creating any moment about the axis, and we don't have any friction. If we had friction, the friction would have been through the page, and that would have created a moment. But a frictionless surface, we are not going to have any moment. So we can write conservation of angular momentum. So conservation of angular moment means that HO1 equals HO2. Definition is R cross MV, the moment of moment, which R is changing. So we call it R here A. We're talking about A and B. So let's name it A and B rather than 1 and 2 to be more accurate. The velocity at A, also R, B, velocity at B. Again, because it's conservation of angular momentum, we don't have any moment. We can cross out M from both sides to make it simpler. R cross V, again, we have two different types of velocity here. The velocity that is tangent, that is going to create a moment, and then VR, which is not going to create any moment. So we need to plug in the right component of velocity. RA is 2. Velocity at A is 5. The sine of the two angle is 1. We can write it or just ignore it. RB, we have the magnitude value. I don't have VB. So that's the only unknown. So VB, if you look at it, would be 10. And the unit system I'm using is foot per second. So that's the magnitude of velocity. But we find the tangential component of the velocity, so we have to write the tangential component. Now we are done with the first part of the problem that wants to find a velocity at b. We found a velocity of b by writing conservation of angular momentum. The second component is asking for the work done on the object. So to find a work, we can write the work and energy equation. We don't have any conservation of energy because the tension in the rope is going to create work for us, so we don't have any conservation of energy, but the work done on the sample will change the energy. So that would be T1, the initial kinetic energy. Oh, let's write it A. The work that is done on the sample will give us the final energy. Initial energy is half m. So the mass, the weight is 8 pounds. Pound is the unit of weight or the unit of force. If you want to find mass, you have to divide it by 32.17 to get slug, which is the proper unit. And v squared, which is 5. That's the only component of velocity that we have at A, equals half. I forgot to write the component of this is the work that is done on the sample. U12 equals half. M is the same, M is not changing. The velocity squared. So the velocity here, I found the tangential component of the velocity here. Also, I know the velocity VR. For energy, the scalar, and I need to put in the magnitude of the velocity. To find the magnitude of velocity, that would be 10 squared plus 4 squared. So in that equation, the only unknown is work. That I find work 11.3 foot pound. And I find work. So if you look at the equation and look at the solution, there are a couple of important points that we need to pay attention. Is that when we read the problem, we need to know what method that we are going to use. The best method to use here is angular momentum, because we have conservation of angular momentum. We don't have conservation of momentum. We don't have conservation of energy, but we have conservation of angular momentum. So we write conservation of angular momentum because none of these forces are going to create a moment. The only unknown here was the velocity at b, but using the conservation of angular momentum, we can find the tangential component of the velocity. So we have to be careful that that velocity that we found is the tangential component. Then the second part of the problem is asking for the work that is done on the sample. So we can use work and energy equation or work and energy principle. We have the initial energy. Energy is a scalar, so it's not directional. We need to plug in the magnitude. So when we plug the magnitude, we have 5. There is no other components here, plus the work that is done on the sample would be the final energy. Half mv squared. V again is the magnitude. The first component, tangential component, and also the radial component. And we find the work that is done by the sample, that is done on the sample. And that's it for the angular momentum topic.